Welcome back. So today we are going to look at key features of graphs. Now this I find really interesting. There's not a lot of arithmetic to do here, so you're really just analyzing and answering questions. That's mostly what we're going to be doing. So in our toolbox today, we've talked a little bit about x and y intercepts, so we're going to use those some more. So first we want to talk about how can you determine whether a graph represents a function. Now we talked about how to determine whether a relation was a function, a set of ordered pairs. So we were looking to see if all of those x values make sure they only had one y value. So another way that we can do this is by the vertical line test. So I'm just going to make up a couple functions. So let's say we've got one that looks like this. Oh, that's not cute. Try that again. Okay, and then let's say I got a curvy dude that looks like that. Awesome. Okay, so when I am looking at to determine whether something is a function, same rules apply. Each x has to have exactly one y. Now we can prove this by doing the vertical line test. And what that means is if I were to draw a vertical line through any point of my function, or my graph I should say, as long as it only hits once, it is a function. Now my problem right here is that this x value, so let's say that's like x when x is -2. Well, when x is -2, it's got a coordinate up here and down here. So we actually have two output values. So this is not a function. All you have to do is find one place where it overlaps and the whole thing is not a function. So anywhere where you draw a vertical line, you should only be able to hit one piece of your graph. If you hit more than that, you do not pass the vertical line test, which means that x, that input, has two different outputs. So if we look at this funky little swervy thing, same thing. If I were to draw a vertical line, I'm going to draw another one because I see how where somebody could get confused. That looks really straight. Okay, that looks better. So when I'm looking at this, if I go to draw a vertical line through any part of my graph, I am only going to go through the graph once. Even with these end behaviors, because this ending, it's going to keep moving over and over and over and over. Now, it might not move over a lot, but it is going to continue going right. It's going to continue increasing. And this side, well, actually, yep. And then this side is going to continue. It's not actually going down because we read a graph left to right, which we're going to talk more about. It actually is increasing as well, even though that arrow points down. Because when we come left to right, we're going up, 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 down, 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 up, 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 down, 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 up, up, up. Okay? But what we're focused on right now is whether it's a function. So if I draw a vertical line through any place, I'm only hitting this graph once. So, yes, this is a function. And this one is not a function. So when we're looking at a relation, when we're looking at ordered pairs, we focus on those x's to make sure each x has one y, only one. When graphically, all we have to do is the vertical line test, because if we only hit it once, then that x only has one output. If we hit it twice, that x value has two, well, or more, depending on what your graph looks like. So let's go ahead and look at our first example. The band director of Eagle Rock High School asks her students to have a car wash as a fundraiser. They are going to charge $7.50 per car. That's an odd amount, but okay. So the graph that represents the situation is shown below. Okay, so just for a little extra practice, since we're with functions, let's go ahead and write a function rule for this. So my independent and dependent variable. So what are we doing? We're charging $7.50 per car. I love when I see per or each. It makes it so easy to set it up. So $7.50 per car. So times C. $7.50 C. Okay. So that is my independent variable. So what are we doing here? We're having a car wash. So, oh, we're trying to make some money. Well, that makes sense. All right. So when we set up our function rule, we're trying to make some money. So money earned. So either M for money or E for earned. So I'm trying to make some money. And how do I make money? Depends on the number of cars that I wash. So the money that we are making per car is $7.50 per car. Cool. Just a little review. All right. So which of the following statements about this graph are true? Select all that apply. So the graph represents a function since every input corresponds to exactly one output. Well, that is the definition of a function. Each input has its own output. Let's see, does that make sense? If we draw a vertical line through any point in this graph, will it only cross once? Yes. So yes, this is a function. The graph has an x-intercept. All right, let's step back. X-intercept. So remember, intercept is like intersect. Where do we intersect an x-intercept? X-axis. So it's where our graph intersects the x-axis. Intersects the x-axis. Oh, I should have put some more space there. So, does this graph have an x-intercept? I don't see anywhere where it has an x-intercept. Why not? Well, wait a minute. Can we have negative cars? Because if we continued this line backwards, that's what would have to happen. We're not going to have negative cars. So this graph does not have an x-intercept. Not true. Nope. Does the graph have a y-intercept? Okay, same thing where the graph intersects the y-axis. You could rewrite all that if you want, but if it makes sense, don't worry about it. So do we have a y-intercept? We do. Huh. How can we earn $250 when we haven't washed any cars? What do you think? Well, did we have money in our account to begin with? Maybe they had money left over from another fundraiser. Maybe somebody just donated $250 because they're awesome. So since with my function rule, I'm making $7.50 per car, you're darn right. Except I already have $250 to start off with. So I need to add $250. Because I need to add that $250 to the amount of money that we've got. So, do we have a y-intercept? Yes, we do. It is 0 to 50. Change of the colors. So the y-intercept represents the amount of money raised by the car wash. So does that $250 represent the amount of money raised by the car wash? This is key. Raised by the car wash. Again, we have 0 cars. So does $250 represent money raised by the car wash? No, that's money we already had or somebody donated along the way. That's not money raised by the car wash. We already have that. So no, it does not. We already have that. So the amount of money in the band fundraiser account represents the input values. Okay, keyword. What's our keyword? Input values. So remember, our input is our independent variable. So who is the independent variable in this case? If it's independent, that means the amount. So the money, if it's independent, then that means cars depends on money? Does that sound right? The amount of cars we wash depends on money? No, the money that we earn depends on how many cars we wash. So is the amount of money in the band fundraiser the input? No, the amount of money we get, that's our output. Now the number of cars washed relates to the amount of money in the band fundraiser account. Yes. That's kind of silly to me. The number of cars washed relates to the amount of money in the band fundraiser account. Yeah, the more cars we wash, the more money we're going to have. Absolutely. Okay. Does that make sense? So when you're looking at these, they're going to ask you about all kinds of things. Now, I do want to point out one thing. There is something super wrong with this graph. And if I wouldn't have just stolen the picture of it, I would fix it, but I couldn't. What's wrong with this line? Remember when we talked about discrete and continuous? Should this be a solid line? Should this be a continuous function? Look at that x-axis. Should this be a continuous function? Can I wash 10.2675 cars? I'm pretty sure somebody's going to be really mad at you if you only wash part of their car. So this should not be the continuous. This should be a discrete graph. So these should be like individual points, not that solid line, because this is not continuous. We cannot find the itty-bitty in-betweens when it comes to number of cars. So sometimes we are given a real-world application where we have a graph that we're asked questions about, and we kind of need to dissect it, break it apart, make sure, see what makes sense and what doesn't. Other times, we're given a goofy looking graph like this. Do not panic, okay? You're given this graph. We're just asked questions about it. So let's go over to our left side questions. And first it asks, yeah, this is kind of important. How do we read and analyze graphs? So when you're reading a graph, you read it just like a book, from left to right. Okay? So you can't just pick random pieces to look at. You need to think about it if you're going from left to right. So first I'm going up, I'm increasing, then I start decreasing, then I jump up here to this goofy little fella. Now look, this is a flat line, so its slope is 0. It's not rising or decreasing, so it has a slope of 0. I can jump up here. Wait a minute, we even have a point down there. All right, that's weird. We'll look at that later. So I go down again, I'm decreasing, increasing, decreasing. So you have to make sure you're looking from left to right, or else if you just look at the arrows, sometimes you'll tell us that we're decreasing when, in fact, from left to right, we're really increasing. That just tells us that that graph continues on and on to either positive infinity or negative infinity. Oh, which brings us to the next part. So on what intervals is the function increasing? Now that word intervals should look a little familiar. So we talked about interval notation. We're going to be using that again. So on what intervals is the function increasing? If you've got colors, please use them because it will make a lot more sense when you're looking back at your notes later if you're kind of color coded. So when I look at my function, again, reading from left to right, where are we increasing? So when I come over here, that was not cute. Let me try that again. All right, so I am increasing, boom, and then I start decreasing. So I'm going to stop there. Now reading from left to right. So again, this has got a 0 slope. Oh, I'm decreasing. Oh, I got this little piece where I'm also increasing again. So intervals where we're increasing. So think about interval notation. Over here, remember, this is continuing to negative infinity. So when I'm increasing, coming from left to right, I'm coming from negative infinity, way, way far away. Negative infinity, where do I stop increasing? Boop, at -2. We're reading left to right, so you're really focused on the x-axis when you're talking about these. So from negative infinity, we come up and we stop at -2. So negative infinity, remember that's a parenthesis, and we stop at -2. Now -2 is a pivot point. It's included in the increasing and the decreasing interval. like, so I can't close it. I need to leave it open because it's included in both intervals. So I'm going to use a parenthesis again. Now we had one other piece, so I'm going to use the little union symbol. So where do we start increasing again? Again, looking at this x-axis, we start at 2 and we stop about 2.5. So again, those are both included in a different piece of our graph, so they're going to stay open. So from 2 to 2.5, we're also increasing. All right, so what's next? It didn't have decreasing? Well, let's go ahead and do that anyway. So why don't you go ahead and pause the video and try and see if you can come up with the decreasing intervals. Okay, let's see what you came up with. So again, we were increasing. So from here, from that -2, I start decreasing again. So my first interval, I started at -2 and I stop at -1. Notice how -1 has an open circle. This is just like when we were graphing inequalities. So the -1 stays open. All right, and then I'm going to keep looking. Again, 0 slope, so that's neither increasing nor decreasing. All right, when I get to 1, I start decreasing again. So I am decreasing from 1 to 2. So I have another piece, so I just use a U. So we start at 1. Again, it's an open circle, so I leave it open. And I stop at 2, which is also included in this other piece, so it stays open as well. All right, last piece, when I keep moving from left to right, I start decreasing again over here. So I start, where's my little union symbol? So I start at 2.5, and I stop at, well, do I stop? I'm pretty sure we just keep going and going. So we go to a positive infinity. So we had 3 different pieces where we were decreasing. All right, let's go back over. So what is the domain? Now these can get a little tricky when it comes to domain and range. So we got to look at our whole graph. So coming from left to right. So domain, remember domain is all of your x values. So my x values, I go from -infinity and then I stop at -1. But do we actually stop here? Because look, we jump up and -1 is still included in our set. So -1 works too. So we keep moving and then we have a 1. Again, that's open. That's open too. So are we stopping? No, because we have that little 1 down there. So 1 is also included. If we keep moving right, we're going to positive infinity. So even though we have these breaks in here, at each of the breaks, we still have a closed circle, which means we're still using that number. So our domain goes from -infinity to positive infinity. You will rarely see it written like that though. Most of the time, you'll see it written all real numbers. Meaning continuous. We can use all those itty-bitty points. All right, so now let's look at our range. I think the range is a little bit different story. So when I'm looking at the range, so we're looking at our y-axis. This end tells me that I am going to -infinity. So does this end. Let's look in between. Well, I do have a point at 0 right over here, so I'm still good. I continue as I guide my pencil up. I still have points. I still have points. I have lots of points when y is equal to 1. I still continue up. Where is the highest point? Positive 2. So the range, if you write it in interval notation, what's the smallest y value? Well, we're heading to -infinity, so -infinity. And what is our largest value? A positive 2. And again, open circle, so you better leave it open. So that's interval notation. Or you can write it in set notation. This is how you're more likely to see it. So set notation, that's the one that had the X with the bar. Well, now we're talking about our y's. So we have all the y's such that y is, well, it's everything less than 2. So the y's are less than 2. So a couple different ways it can be written. Unless it specifically states which way to write it on a test, I don't care, whichever way you're comfortable with. However, if it's multiple choice, you need to make sure that these make sense to you when you see them. All right, are we done? There are exactly 2 relative minimums, true or false. Oh no, sorry, maximums. I should probably highlight my keywords. All right, so relative maximums. Well, let me teach you what that is. So a relative maximum, when we're looking at our graph, going left to right, this pivot point right here, that is at a peak. I'm increasing, then I start decreasing. This is what we call a relative maximum. Now, yes, it has to go from increasing to decreasing, okay? It has to be at a peak. If it stopped there, it would not be a relative max, okay? It's got to have that pivot point to it. So let's look for any other pivot points that we had. So again, this piece right here had a slope of 0, no pivot points. That little dot's just by himself. So let's come over here. So I'm decreasing, then I'm increasing. So this pivot point is not a relative max, it is a relative min. Notice it's not the minimum of the graph, it's just a relative min. For this piece, it is a minimum to the pivot point. So again, up here we have a pivot point, so we're going increasing to decreasing. So this would be a relative maximum. Okay? So there are exactly 2 relative maximums. Well, we just spotted them both, so that is true. All right, hope that all made sense. Let me know if you need anything.